So let us see the concept of inductor. So in the earlier class we were discussing the what is inductor, and what inductor is a device that opposes the change in current. Now let us see the properties of inductor here. Okay, so what is the voltage across inductor we have derived, that is V equal to L into di by dt. Okay, this is voltage across a inductor. Okay, this is inductor L and the voltage across inductor V is equal to L into di by dt. Okay, so in order to find the current through the inductor, how can you find the current here? Because it is in derivative form, you can integrate it. Okay, for that we are shifting the other factors to an opposite side, that is di will be equal to V by L times dt. So by integrating it over a period of t, 0 to t di will be equal to 0 to t V by L into dt. So integration derivation will be get cancelled, so that will be left with I equal to V by L times t. So this is the current through inductor. Current through inductor. Okay, voltage across inductor is V is equal to L into di by dt, and current through inductor is V by L into t is the time in seconds. Okay, now let us see power absorbed by inductor. So ideally the inductor will never absorb any power, but practical inductor will have some resistance that will consume some power. So what is the power? Power absorbed by inductor. So we already know that what is the expression for power? Power equal to voltage into current, right? So what is the unit of power? That is watts. Okay, so here what is the voltage expression across inductor? VL is L into di by dt. We already know that. Okay, so by substituting the expression for voltage, that is L into di by dt, okay, into I, since V equal to L into di by dt. Okay, so this is power absorbed by inductor, L times I into di by dt. So this is the power absorbed by inductor. Okay, now let us see what is the energy stored by the inductor. Okay, so I forgot to mention in the previous class that our inductor will absorb energy in the form of magnetic field. Whenever our inductor is supplied with a AC supply, AC is nothing but alternating current. Okay, whenever our inductor is excited with a AC supply, our inductor will induce some flux around the coil. So this is a flux, that is pi here. Okay, and there will be number of turns. Okay, you can see it is twisted into number of turns. It is first turn, second turn, third, fourth, fifth, and it is n turns. So the number of turns is indicated with n, that is number of turns. Okay, and it is I is current through inductor, I is current, and pi is flux. Okay, if you pass some AC current through number of conductors, some flux will be induced across the inductor. Okay, so this magnetic flux will store energy in the form of magnetic field. Okay, our inductor will store energy in the form of magnetic field. This is important. Okay, our inductor will store energy in the form of this magnetic field. Okay, this is about inductor. So inductor stores energy in the form of magnetic field. Okay, whenever it is excited with AC, some energy will be stored by this inductor. Okay, whenever our supply is absent, this stored energy will be supplied to load, that is nothing but a resistor. Okay, first of all you have to excite the inductor with a source AC supply. Okay, that will store some energy. Okay, whenever we disconnect our AC supply, the stored energy in the inductor will be delivered to load. Load is nothing but resistor. Okay, so this is the phenomena. Okay, this is important. Inductor stores energy in the form of magnetic field here. Because why it is important means, our capacitor, which I am going to explain in the next class, capacitor stores the energy in the form of electric field. Okay, there are two types of field here. Okay, magnetic field and electric field. Our inductor will store energy in the form of magnetic field, but capacitor will store in the form of electric field. Okay, inductor will store the energy in the form of magnetic field, capacitor stores the energy in the form of electric field. So this is the difference. Okay, so from this I can derive the value for inductor, that is number of turns into flux by current through the inductor, that is L is nothing but n pi by I. Okay, n is number of turns, pi is flux, and I is current. Okay, so this is L. You can substitute the value of L here. Okay, L equal to n pi by I. This is one important question. Okay, so this is about inductor. Let us take a problem. Let us derive the energy consumed by inductor. Energy means nothing but power into time. Okay, some amount of power will be lost in some period of time is nothing but energy. Okay, that is nothing but energy consumed by any element. okay, power into time. Okay, so let us take, we know that energy is nothing but integral of 0 to t into p dt. Over a time period, what is the amount of power absorbed by the element is nothing but energy. Okay, this is nothing but our energy. What is p here in the previous derivation, that is L into I into di by dt. Okay, so let us substitute the value of p here, that will become 0 to t, okay, L into I into di by dt into dt. Okay, this dt will get cancelled, so we will be left integration with respect to current I here. Okay, now it is integration with respect to I, so we can take out the L which is constant here, I into di. So integration of I with respect to di will become I square by 2. Okay, integration will become I square by 2, that is L I square by 2. So what is the energy absorbed by inductor, that is 1 by 2 Li square. Half Li square is the energy consumed by the inductor. Okay, this is energy stored by inductor, not consumed. Energy stored by inductor in time t. Okay, in some time t, what is the energy stored by inductor? In the form of magnetic field. So how inductor stores energy? In the form of magnetic field here. Okay, so what is the magnetic field energy that is stored by inductor? That is given as E equal to 1 by 2 L is inductor, I is current. Okay, L is inductor, I is current. Okay, energy stored by inductor is E equal to half Li square. This is important. So before going to understand inductor or capacitor, we need to understand what is open circuit and what is short circuit. Okay, so first of all, what is open circuit? Open circuit means whenever we have a source and a load, but the circuit is not closed. That means the switch, this is switch S, the switch is not closed here. That means there is no current flow. That is, there is no current flow I. That means open circuit means the current in the circuit is 0. Okay, now let us see what is short circuit. Short circuit means the circuit is closed here, but the voltage across a short circuit is 0. Okay, voltage across a short circuit is 0. Whenever a voltage across any element is 0, that is treated as short circuit. Whenever current across any element is 0, whenever current in the element is 0, that is treated as open circuit. Okay, whenever if current is 0, that is treated as open circuit. If voltage is 0 across any element, that is treated as short circuit. Okay, now let us see the observations in inductor. So before going to observe inductor, now let us see these two sources. This is the symbol for AC voltage source and this is symbol for DC voltage source. Okay, here you can see this bigger plate is positive plate and this is negative plate. Okay, there will be another parameter, that is a capacitor, which has equal distance. Okay, but here it is having one is higher and one is bigger and one is smaller. Okay, this is a voltage source, this is a capacitor. Okay, this is a AC voltage source, this is DC voltage source, this is a capacitor. So okay, these three are the things to be remembered here. Okay, now let us see the observation in inductor. Now let us observe whenever we are going to excite our inductor, what is the behavior of inductor. Okay, this is a circuit which is having a apply and a switch S and inductor L. Okay, so in the first case switch S is open and we know that voltage across inductor VL equal to L into di by dt. Okay, now let us see when switch is off, that means the circuit is open circuit, that means there will be no flow of current and there will be no voltage across inductor. Okay, there will be no voltage because there is no current. Now let us see, I am going to turn on I am going to close the switch so that some current will flow in the inductor. Okay, just after closing the switch, there will be a minute current, that is differential current di, flow in the inductor for a short period of time at 0 t dt equal to 0 plus. For a very short period of time, some amount of current will try to flow in the inductor. So now what is happening to the voltage expression? Okay, V equal to L into di by dt. So there is some fraction of current that I am treating just 0.001. So dt is almost 0 plus means 0. So what is happening is 1 by 0 form. Okay, 1 by 0 is nothing but infinite. That means voltage across inductor is infinite for whenever we are going to turn on the switch. Just after turning on the switch onto a inductor, the inductor voltage will be behaving like infinite. Is it possible practically? Infinite amount of voltage across a single inductor? That is not possible. Okay, so that's why in order to make it impossible, our inductor doesn't allow sudden changes in current. Okay, if there is no sudden change in current, this di will be equal to 0. Di will be equal to 0 means the voltage across inductor will be not infinite, it is 0. Okay, so practically it is possible, 0 is possible. That means inductor voltage across inductor is 0 means I am going to make it as short circuit. I already told you voltage across any element is 0 means that element is short circuited. That means this is nothing but voltage equal to 0. This is nothing but short circuit. That's why our inductor doesn't allow sudden change in magnitude of current. Okay, this is why our inductor doesn't allow magnitude of change in magnitude of current. Okay, Now what is this means? Inductor will behave like opens even after switching the current. That means there will be no flow of current even after switching on the switch. Okay, this is about turning on the switch. Now let us see, switch is closed for some time. After some time, what is happening? The current will start flowing. After some time, the current will start flowing in the inductor. Okay, so some current will flow in the inductor. So this current will cause some flux production in the around the inductor. So some flux will be produced. That is L equal to number of turns into flux by current I. Okay, so some flux will be established around the inductor, so that some amount of energy will be stored in the magnetic field. This is the magnetic field around the inductor, so some amount of energy will be stored in this magnetic field. So this is about after some time. Now let us say our DC current. Let us apply DC current of 5 amperes. This is the symbol for DC current. Okay, this is symbol for DC voltage and this is symbol for a current source. Okay, now let us apply a DC current of 5 amperes. Okay, magnitude is constant for a DC, right? Magnitude is constant. Steady current is nothing but DC current. That means if this is my I and this is V, this is constant. Okay, this is T, right? This is steady current. Okay, this is constant throughout the time. 5 amperes is constant. That means there is no dI by dt. So I am going to apply a 5 amperes current to our inductor. Now what is it happening? dI by dt will become d into 5 by dt. So for a constant, derivation is 0. Okay, so our voltage V will be L into dI by dt is 0 here. That will become 0. That means the voltage across inductor will be 0. Okay, we will be doing some problems on this. Now let us take a problem so that you can understand the concept betterly. So this is the question regarding inductor. So what is the question given? The current in a inductor rises at a rate of 2 ampere per second. Okay, the rate of rise of current is 2 ampere per second. Then find the voltage across inductor and the energy stored in the magnetic field after 2 seconds. So this is the question. So what is the thing which we need to understand is, here the current in a inductor rises means improvement from time to time, is at a rate of 2 ampere per second. That means for every second 2 amperes of current is increasing in a inductor. Okay, that means we know that it is a non-linear element V and I, so it is like this. So the increment, the dI by dt is nothing but this one. For every 1 second, the increment in the current is 2 amperes. That means I can write it as given data. The given data is rise in the current is nothing but dI by dt, change in the current dI by dt. This is what he given, that is 2 ampere per second. So using units also you can find the dI is amperes, dt is seconds. Okay, this is dI by dt data. Then he asked us to find is voltage across inductor VL, which is nothing but L into dI by dt. Okay, this is voltage across inductor, and energy stored in the magnetic field after 2 seconds. That means energy stored by inductor is given as half Li square. We know that. Okay, he given it at t is equal to 2 seconds. So this is what he given. Okay, he is asking us to find voltage across inductor and energy stored in a inductor. And I forgot to mention, this is inductance value is 2 Henry. The unit of inductance is Henry, right? He given a inductor of 2 Henry. That means L equal to 2 Henry. Now let us find solution. So what is the first question? That is voltage across inductor. That is VL, which is L into dI by dt. So VL, first question, VL is equal to L into dI by dt. Okay, just substitute the values here. L equal to 2 and dI by dt is 2. So the voltage across inductor is 4 volts. That's it. Now let us find the second problem. Here we don't have the value of current I. So how can you find this? So using this data here, dI by dt is equal to 2 he given. Okay, so in order to find I, you can keep the dI here and shift the dt to opposite side. So apply some integration on both sides. So you get I equal to 2 times t. Okay, if you can apply integration, derivation and integration will get cancelled. You will left with I equal to 2 into t. So what is the value of t he given? He given value of t as 2. So the current is 4 amperes. The current in the inductor is 4 amperes. So that is how you have to find. Okay, what is the value of current now? So E equal to half Li square, energy stored in a inductor, energy stored in a inductor at t equal to 2. So this is the answer. So that will be equal to 1 by 2 into L is 2 here and I is 4 square. Okay, that will become 2 to get cancelled, that will become 16. What is the unit of energy? That is joules. So what is the energy stored in an inductor? What is the energy stored in an inductor after t is equal to 2 seconds? It is 2 Henry and current is 4 amperes. Okay, in a magnetic field it stores 16 joules at 2 seconds. Okay, voltage is nothing but voltage. What is the voltage across inductor? That is 4 volts here. Okay, at a 4 volts voltage across inductor and a current of 4 amperes, a 2 Henry inductor will store energy of 16 joules after 2 seconds. So this is the idea. Okay, so with this I am concluding inductor. Let us go for capacitor. Will act as short circuit. It is not open circuit. Okay, VL is 0 means it is short circuit. VL is 0 means short circuit. Just after switching there will be so inductor will doesn't allow sudden changes in current means I is 0 even after closing the switch. That means inductor will act as not short circuit, it will act as closed circuit. Sorry. So in this case, in the second case, I told it was short circuit, but it is open circuit actually. Okay, no problem. Short circuit. Inductor is 0. So just after switch S is closed. So just after switch S is closed, the inductor doesn't allowing any current. That means the circuit is staying open circuit. Even the switch is closed, the circuit is open circuit. No current will flow at 0 plus time period. Okay. So when we are going to apply DC supply, the circuit will behave short circuit. Okay. Inductor will behave like short circuit when we are going to apply DC voltage. Okay. So this is the idea. Okay. Now let us take a problem on inductor.